Okay, so I want to start off where we left off, and just as a reminder, we had as a hypothesis that xn is a Cauchy sequence of real numbers, and the claim is that there is some real number L to which the sequence xn converges. So remember, the idea here was basically we wanted to prove that Cauchy implies convergent in R. So that was our motivating idea here, right? We're trying to prove the equivalence of complete with respect to Cauchy sequences and complete with respect to the least upper bound property. Okay, so we started off our proof by defining this set X, which is the points in X are the terms of the sequence. And the first claim is that X is bounded since our sequence is Cauchy. So let's look at this and we'll say, in fact, since X is Cauchy, or since Xn, our sequence Xn is Cauchy, for epsilon equal to 1, there exists some integer n, that's a counting number, such that n and m bigger than or equal to n implies that the distance between xn and xm is less than 1. Okay? But this means that in particular, for that n, if n is bigger than or equal to n, then the distance between xn and x big N is less than 1. So n bigger than or equal to n implies that the absolute value of x sub n is less than or equal to the absolute value of x sub big N plus 1. Okay? Now, let m equal the maximum of, this is supposed to be curly bracket, the maximum of x1, the absolute value of x1, the absolute value of x2, all the way up through the absolute value of xn minus 1 and 1 plus the absolute value of xn. Okay, so with this is our choice of m, then for all n of natural numbers, for all n, the absolute value of xn is going to be less than or equal to m. So notice the way to kind of think about this is, remember, if we have x1, x2, x3, and then at some point we've got xn plus 1, so forth and so on. So for all of the terms back here, we know that the absolute value of xn plus k, say, is less than or equal to 1 plus the absolute value of xn. That's 1 plus the absolute value of big Xn, right? Because we got that from our terms being Cauchy. Okay, and then now, if n is over here, so if n is less than big N, then definitely the absolute value of xn is going to be less than or equal to m, because m is the max of all these terms. Okay, so if we choose that as our big M, then we now know that the terms in our sequence are bounded, and that means that our set X is bounded. Okay, so Xn belonging to, well, that's being redundant, so we'll just say so X is bounded. In other words, every element of X lies in the interval negative m to m. Okay, so that's the conclusion of step 1, is that X is a bounded set. Now, step 2 for the proof is going to be to consider another set, and this other set is going to be defined as follows. So we're going to define T to be equal to the set of real numbers such that xn is bigger than or equal to t infinitely often. In other words, T belongs to big T if and only if there exists infinitely many values of n such that xn is bigger than or equal to t. So picture-wise, what we're saying is that infinitely many of the terms x sub n are bigger than or equal to t. And if that happens, then that t belongs to our set big T. Okay, so observe. The first thing we want to observe about this set T is that T is bounded above. Now, why is T bounded above? Since T belonging to T, if we have an element of T, then that element obviously has to be less than or equal to M, right? Because remember, all of the terms of our sequence are less than or equal to M in absolute value. So if you have infinitely many terms of the sequence greater than you have to be less than or equal to M. Okay, so that's the first fact about T. The second fact is that T is non-empty. So let's put that. T is non-empty. Now, how do we know T is non-empty? Well, negative M belongs to T. Because remember, every element of X lies in this interval negative M to M. That means that all of the terms of our sequence are greater than or equal to negative M. So that means that negative M definitely satisfies this property, right? The X sub n are greater than or equal to negative M infinitely often. Okay, so this means that T is non-empty, T is bounded above, therefore we can use the theorem 2 to say by theorem 2, right, since T is bounded above and non-empty, there exists a least upper bound that is a real number. So let's call it B. So we're saying sup of T exists and is a real number. So let's define B to be equal to sup of T. Okay, so we have step 3 now, which is the claim that our sequence xn, which is Cauchy, actually converges to B. So we'll have step 3, which is going to be, we claim that xn goes to B as n goes to infinity. Okay, now what do we need to do to prove that xn goes to B? We need to show that for every epsilon greater than 0, there exists an index n such that n bigger than n implies the distance between xn and B is less than epsilon. That's what we need to show, right? That's what we want to show. So let's go on with our proof here, and we have to say let epsilon greater than 0 be given. Now, since xn is Cauchy, so since our sequence xn is Cauchy, there exists some index n, let's call it n2, such that n and m bigger than or equal to n2 implies that the distance between x sub n and x sub m is less than epsilon over 2. Because remember, that's what it means to be Cauchy, is regardless of if you have any positive number, then when you go far enough in your sequence, all of the terms are within epsilon units of each other. So we're going to use epsilon over 2 as our positive number, and we've got an index n2. We're guaranteed to exist, that there exists some index n2, where all of the terms past n2 are within epsilon 2 over 2 units of each other. Okay, so we know we've got that. But now watch this. Another thing is that if b is the supremum of t, then that means that b plus epsilon over 2 cannot be in t. So let's put that in here. Note that since b is the supremum of t, that means that b is an upper bound. So b is bigger than or equal to every element of t. B plus epsilon over 2 can't be an element of t, because how is b going to be greater than or equal to b over epsilon over 2? Impossible, since epsilon is a positive number. But what does it mean when we say that b plus epsilon over 2 isn't an element of t? Let's go back to our definition of t. What is t? What does it take to be in t? T is the set of real numbers such that x sub n is greater than or equal to t infinitely often. So if b plus epsilon over 2 doesn't belong to t, then that means that it's not the case that the x sub n's are greater than or equal to t infinitely often. In other words, we've got the negation of there exist infinitely many values of n such that x sub n is greater than or equal to t. So that means that only finitely many of the terms of the sequence are greater than or equal to t. So this means that, so we need the negation of there exist infinitely many n such that x sub n is greater than or equal to t. Now, if we negate that, we're saying that it's not the case that there exist infinitely many. And what does it mean to say that it's not the case that there exists infinitely many n? That means all but finitely many of the n satisfy x sub n is less than or equal to t. So the negation of this is all but finitely many. What's a good way to say that?
It's 1630.
Thank you. A good way to say all but finitely many.
It's 430.
Thank you. Okay, so what about this? There exists an n3 in n such that n bigger than or equal to n3 implies x sub n is less than t. Okay, so what I'm saying is, it's not the case that there exists infinitely many n indices where the terms are bigger than or equal to t. So for us, remember, our t is going to be b. So let's say this means there exists some index n sub 3 such that n bigger than or equal to n sub 3 implies xn is less than b plus epsilon over 2. So sorry, that should be epsilon over 2. Because we're saying that b plus epsilon over 2 can't be an element of the set t, because b is an upper bound for the set, right? So b's got to be bigger than or equal to every element in that set t. Okay, so let's clean this up a little bit. Okay, so the last thing I want to note here is note that since b is equal to the supremum of t, right, that means that b is the smallest upper bound for t. So we'll say since b is equal to the supremum of t and epsilon over 2 is greater than 0, b minus epsilon over 2 is not an upper bound for t. Now, what does it mean to not be an upper bound for t? That means that there exists some element of t that is bigger than b minus epsilon over 2. So in other words, there exists some, let's say there exists some s in t such that s is bigger than b minus epsilon over 2. This is what it means to say that b minus epsilon over 2 is not an upper bound for t. Okay. Well, now, if there's some element of s that is bigger than b minus epsilon over 2, that means that infinitely many, so let's put it here for that s, infinitely many, infinitely often, the terms of our sequence are greater than or equal to s. So say, so for that s, for that real number s, infinitely many, or xn is bigger than or equal to s infinitely often. Okay, so let's kind of draw a picture of what's going on. Okay, so we've got b. We want to show that there exists some index n after which the terms are within this interval, b minus epsilon to b plus epsilon. So to give us some space, some wiggle room here, we said let's look at the smaller interval. And our smaller interval here is just going to involve, so we're going to look at just b minus epsilon over 2 to b plus epsilon over 2. Okay? And now within this interval, we said, first of all, that this b plus epsilon over 2 is not in t, so there can only be finitely many indices for which the terms of the sequence are greater than that. So we've got infinitely many back here. We don't know where they are, but they're strictly less than b plus epsilon over 2. Okay, so in fact, we said that n bigger than n, 3, implies xn is less than less than or equal to b plus epsilon over 2. Okay, so we've got a whole bunch of them back here. And then we said that b minus epsilon over 2, b minus epsilon over 2 is not an upper bound. So there exists some point s, so maybe that's s. Remember, s is going to be less than or equal to b because b is the supremum of t. So since s is in our set t, that means that infinitely many of the terms have to be bigger than s. But remember that the terms of the sequence are also less than or equal to b because, no, they're not necessarily less than or equal to b. Just kidding. But we do have infinitely many of the terms greater than s. So here's what we're going to do. Since infinitely many of those terms are greater than s, then that means that there's some index that's bigger than n3. So there's some point, right? So maybe it's like x sub m, right? So remember, for that real number s, xn is bigger than or equal to s infinitely often. So find some m, some index m that's bigger than n3, and x sub m is going to be, on the one hand, going to be bigger than or equal to S, which is bigger than B minus epsilon over 2. But on the other hand, it is going to be less than or equal to B plus epsilon over 2. Okay? So we've got it less than or equal to B plus epsilon over 2. And now that is going to be our n. So now what we will say is n bigger than m implies that the distance between xn and b is less than or equal to the distance between xn and xm plus the distance between xm and b. Okay? In fact, let me just kind of copy this. Because, so we need to do one more thing, which is going back. Oh, that's exactly what I needed to not erase. Okay, that's what I wanted to erase. So back here, let's go back to here. So what I want is I want to choose an m, right? So there exists an m. And first I want the m to be big enough. I want an m. So we're saying choose m, big enough so that number one, m is going to be bigger than n3 so that we can be guaranteed this half of the inequality. And number two, I'm going to say choose it so that m is bigger than n2 because that's going to be important. M is bigger than n2. Okay, so now since I know that m is bigger than n2, if n is bigger than m, which is bigger than n2, that implies that xn minus xm, the distance between x sub n and x sub n, is less than epsilon over 2. So we've got this part right here is less than epsilon over 2 because of Cauchy-ness. Okay, and then what about the xm, the distance between xm and b? Well, xm is bigger, right? Xm, this is the key right here. Xm is in between b plus epsilon over 2 and b minus epsilon over 2. So that means that the distance between xm and b has to be less than epsilon over 2. Okay, so that is less than epsilon over 2 since m is bigger than n3. Okay, so putting it all together, n bigger than m implies the distance between xn and b is less than epsilon because we'll have epsilon over 2 plus epsilon over 2, so it's less than epsilon, right? And so for any n, isn't that what we wanted to choose? For any epsilon greater than 0, there exists an n. We ended up using little m, such that n bigger than little m implies that the distance between that term and b, which is our limit, is less than epsilon. Okay, so that is the end of the proof. And as a conclusion, we've got Theorem 6. Theorem 6 is the Cauchy convergence criterion for sequences. And it says a sequence of real numbers, let's say a sequence a sub n, converges to a real number if and only if for every epsilon greater than 0, there exists an n, an index n, such that n and m bigger than or equal to n implies the distance between xn and xm is less than epsilon. Okay? So this is a way of saying that in R, since R is complete with respect to Cauchy-ness, Cauchy sequences are convergent.